Hello, my name is Alex Useche, and this is my presentation on radare2 in gophers, analysis of Go binaries with radaring. So let's go ahead. Alright, so really quickly about me, go by hex0punk, name Alex Useche. I'm a security engineer at Bits, and I previously worked as an application security penetration tester, mainly focusing on IoT and mobile, and a lot of web as well. Yeah, before that I was a software developer for several companies. I'm also a Go aficionado and a Rust fan. I love messing with binaries and code, and I'm a father and husband as well. Great, so what is this about? We're going to basically introduce you to the basics of reversing Go binaries and how to work with Go binaries with radare2. So we're going to learn what makes a Go binary different than a C or C++ binary. We'll be identifying techniques for conducting binary analysis of Go binaries. We'll also be identifying common concurrency patterns in Go binaries. We'll be using Go tools to make your radare2 analysis more effective. Now I'm going to assume some knowledge of Go, but I'll try to just cover some of the basics as we go, just to try to, just in case maybe this will interest you not only in reversing Go binaries, but also in writing Go. So first of all, let's learn about the Go assembler. The Go assembler is based on the input style of the plain 9 assembler. So it works on a semi-abstract instruction set. Now, what that means is that the output that you see in tools and using the internal Go tools might not always be a direct representation of the machine code. For instance, you might see a move instruction, which might actually be a load instruction, right? So it also introduces a set of pseudo registers, which we'll look into in just a moment, and introduces a set of directives used by the garbage collector. We won't dive too deep into the directives. I will mainly take a look at the pseudo registers. So these are the Go pseudo registers introduced by the assembler. So when you use tools like Go tool obj dump, you're gonna see output like this, and in the output you might see some of these pseudo registers. So some of them are gonna be pretty obvious. So you have FP for the frame pointer, which it's used as to reference arguments and local variables. PC will be your program counter. There is a pseudo register called the static base pointer, this one over here, indicated by SB. It's used to name global functions or data based on memory origin. If you have worked with MIPS architecture, you will have seen, you'll probably be familiar with this a bit. It's similar to the GP register in MIPS architecture. So for instance, right here we have a little bit of assembly from using the Go tools, and we have a call to runtime new proc, and in parentheses we have SB, the static base pointer. What that's indicating is that the new proc function is a function named runtime new proc as an address in memory. So it's an static base in memory. Then we have SP, which is basically your RSP, just typical stack pointer indicating the top of the stack. And then BP, which is your RBP, same as RBP, your base pointer. And you might see EXO register, which is just a full 16-byte register. Now, tooling. It is a great idea to complement your work with when you're working with Radare and Go binaries with additional tools that are part of the Go toolset. So mainly you want to use this tool called Go tool obj dump. You will usually have to install Go, and then you have a set of tools. If you type Go tool, you'll see this whole list of tools. One of them is obj dump. It will disassemble Go binaries for you as long as they aren't stripped of symbols. So if you use the uppercase S flag, you will see Go code. Typically, you will see line numbers next to the assembly code, which is pretty useful. You can use the lowercase s letter to specify a function, and Go will actually, the tool will actually do a grep-based search on the function name that you indicate with a flag to disassemble that particular function for you. This is also helpful for grouping a set of statements to a line of code, this particular flag with the uppercase S, since we can see the line line numbers associated to different assembly statements. It is going to print left to right instructions, so similar to the AT&T, so basically like the AT&T syntax. And it is not an option for stripped ELF binaries, as I mentioned. However, even if you strip binaries, if you stripped a binary, a Go binary in Mac in a Darwin architecture, you are going to see you're still going to be able to use this tool, because the internal tools, as we see later, are not the Go tools are not great at stripping symbols from Go binaries. So it's a match made in hacker heaven, really. The Go tool, being able to use Go tool obj dump alongside with the with radare2. So if you type Go tool obj dump, here we are passing it the function main.main, and this, by the way, will be the main, what the main function is called in Go binaries, how you will locate it, and we are passing it the uppercase S flag so that we can see this nice line numbers. So basically we can group all these assembly instructions to one line of code, which is very useful, like I said, and this is the name of the binary. So as we see, the output is pretty similar. There are some small differences, like for instance, we have the SP, SP pseudo register, we have the BP pseudo register, but we already went over those, and those are pretty easy to determine by looking at this. So we have RSP and we have RVP, so pretty simple. Now, if you're using Go 1.15, which was released just 3-4 weeks ago, was released, I believe, August 11th, the last August 11th. So if you run Go tool obj dump, this is what you're going to see. So you are not going to see the line numbers, but you are going to see actual code. And for the most part, it does a pretty okay job in matching code to assembly instructions. And again, this is super helpful, in particular if you're working on a macro architecture, or if you are working with binaries that are not stripped of symbols. And this is just in 1.15, there is a flag that you can pass it, which allows you to see the GNU instructions as well in AT&T syntax. So the new flag is tag GNU, and you will be able to see the instructions like this as well. Pretty nice as well, I think. Now, looking for strings. So Go compiles the strings a little bit different than other binaries in that it compiles, let's first look at this. So if you are looking for a string in the text section using Radare, and we use IZ to look for in the text section, and we look for the word human, we don't get anything. However, if we look for the entire strings in the entire binary, that's when we get a result, and we have our word human here. Now, the same thing happens if we use radare2. If we just pass it the C flag to look for just in the text section, if we grab for human, we get nothing. If we search the entire binary, then we get the string that we're looking for. Now, if you observe in this last screen right here, this is just our radare2 output, and we see this, we look for the word Abed, which is a name, Abed Nadir. So here's the string Abed Nadir for the value of a string variable. It is easy to read here, however, it is clumped together with a bunch of other strings that have nothing to do with the value of that particular variable. Now, why is that? That's because Go does not store null terminated strings. It clumps them all together in the text section. It uses that separate table with string length information so that Go can look for that section, and then based on the length, then it prints that particular string. That means that it can be difficult to find cross references. And again, this has to do with how the reason for that is simply because of the way that Go compiles strings in your binary. So it can be difficult to look for cross references, in particular because, let's say your string is hello world. Go might decide to store the word hello in a clump and a blob uh, of text, of strings, and then the word hello on a different blob of text. So that can make a few things working with strings a little bit difficult in some occasions. Not a huge deal. It's just a nature of how Go works with strings again. Now you can use some tools like this one, which is a nice tool that uses the radare2 API for Python to be able to do a little bit faster string searches if you want to focus on that. And again, search for strings in the entire binary, not just the text section if you are interested in searching for specific strings. Functions. So in Go, we have this particular structure. So we can call, we name the package, and then we can declare a structure. Now we can also associate a method to this structure. So not just a function, but a method that is associated to the structure using this particular syntax. Now in this case, we indicate that the receiver is indicated by, it's a pointer to the debugger struct, and then the name of the function is a start target. So how do we identify that in radare2? The best way to do it with radare2 is following this particular syntax. If you're using other tools for reverse engineering, you might see this structure, package, the name of the package, then the name of the function, or package dot, the name of the receiver structure, and the name of the method, or package dot, this is in the case of radare2, we have underscore underscore receiver struct underscore underscore dot method. So like here, we have the name of the package, which is this whole github.com/terminal/code/debugger. Debugger is the name of the package. The debugger right here in the underscore, that's the name of our structure, which is indicated here. And then start target is the method. If you notice, it's using Pascal case and then camel case in these instances. If you're familiar with Go, the functions that are named with Pascal case are exported and are publicly available to other structures and other packages. And that's not the case when using camel case. In that case, the function is not exported and therefore is private. So pretty simple, again, to identify functions in not strip binaries, and even in a lot of strip binaries that are stripped using the Go tools. Like here, we have the name of the package, and then we have the name of the structure, and we know that this is the name of the function. So this is the name of the receiver, and this is the name of the function. So pretty easy and handy to look for this particular syntax when identifying functions. If you're looking for C Go functions, so you can write C within your Go code. This is the syntax that you're usually going to see. So underscore cgo or underscore cpunk. And then the nice thing is that if you, so for instance, right here I wrote a custom function called greet, and within that function I called the C function free and the C function malloc. The nice thing is that I didn't have to create new functions for those, even though I'm only making use of these functions. They're also being listed. All the functions that C functions that you use are going to be listed when searching for functions in Radare. So that's pretty nice as well. Now let's look at the how the prologue for Go binaries works. So Go routines have a small stack by default. All Go routines, all Go functions have a small stack by default, and that's typically 2048 bytes that has been growing as Go keeps evolving. If you look at the source code for Go, that's indicated here in this variable, stack min, that's the minimum size of the stack of any function in Go. And because of that, Go routines will call more stack, this particular function from the runtime, to grow the stack as needed using this technique called stack copying. This is because Go can be sure that a function will grow the stack. For instance, if you are calling a function asynchronously using gophunk, you call the gopher, for instance. Given that the routines are not deterministic and they can be potentially be called recursively, Go cannot be sure that the function will outgrow the stack. So then because of that, each function at the beginning of the function has this prologue where it is actually comparing the stack pointer against this variable called stack guard to check for overflow. And then when this occurs, the stack grows and the pointer in the stack are the pointers in the stack are updated, right? So it starts. This is what you're gonna see in the beginning of most functions in Go, where it's actually doing that comparison, and then it's gonna go in a loop and call more stack as needed to grow that stack for this particular function. And that's one way that you can identify functions in Radare. Or for Go binaries, is that you can identify this particular prologue. If you want to experiment and play with the stack, how Go handles the stack, you can write some Go code and prefix your functions with this pragma, the Go no split, and you will basically tell the Go runtime to not do stack splitting. So it's a pretty interesting way that Go handles stacks, and that enforces protections against stack overflow as well. Now, let's look at some conventions. The return values are placed in the stack as opposed to C, where return values are placed in the register. So for instance, here we are at the end of a function. We're about to return from a function. So we are moving a false value, the 0 value here in the stack. And then we returning. Then we restore the stack, and then we return. So that value is stored in the stack rather than in registers, as opposed to C, like I mentioned. Same thing as arguments for functions. They are always moved to the stack rather than registers. Right here, we're calling the function check password, and two things are happening. We are basically just passing it a string. So we're checking the password as a string, and so we're passing the value of the string, and we're passing the length of the string, because that's how strings work and Go. Now, one very useful way, and this is going to be the key to reversing reversing Go binaries in Radare. It's going to be to identify the underlying language constructs. Basically, when you strip functions, stripping functions in Go is not easy. You can use this syntax, go bill ld flags, and you pass it these two flags to strip the binary. However, typically that only strips the dwarf symbols table, and we're left with all the dynamic symbols. So because of that, a lot of times when you work with a Go binary, you're actually going to see all the functions nicely in your radare2 output. So it helps to become familiar with common functions from the Go internals. So mainly these have found very useful to be familiar with these functions and know what they do. So source runtime, source IO, source net, and source OS. This is again the key to reversing Go and concurrent code in particular, because we will be able to use knowledge of these functions to identify when certain functions are called in an asynchronous manner as Go routines. And we will identify a lot of what's happening in your code by being familiar with the code. So now, and this is just a side note here, that if you really want to strip your binaries, your Go binaries, the best tool that I have found is UPX, which really strips the function names. It leaves very little for you to be able to work with, and then it significantly reduces the size of your binaries. So that's just a side note there. Now, let's look at some examples of Go internal variables. For instance, if you have a function like this, and we do this function is called deref_copy. Here is we are dereferencing the receiver, which is signified by the variable s, and we are assigning it the student pointer, which we also dereferencing. So in this case, what's going to happen in the disassemble code, what you're going to see is this call to sim runtime.typed menmove. So when you see that, you know that there is a receiver somewhere in your code where the receiver is being dereferenced. Now, this is a low-level function, the type menmove that you can see in the source code. This is where it's actually located in the Go source code, source runtime and barrier.go. And this particular file has a lot of functions that have to do related to the garbage collector in Go. So in this case, we learn a couple of interesting things. One is that the source variable is actually passed as an unsafe pointer. So that, if you are working in security, that it should already be pretty interesting. And here, if we read the comments, it's indicated that there is a race here. So if you see a type mem move call, you can potentially start testing for race condition issues. Because the source pointer might be reassigned before this operation happens right here, right? Now, if you want to identify when a function is being called as a go routine, then we look for sim.runtime.newproc. So in this case, we have copy print ln, and we're passing in the variable test, and then we call new proc, and we're passing, and if we look at the definition for the function, it tells us that the new proc function creates a new go routine function with a particular and it's pass a variable that indicates the size of that function in byte, the size of the arguments in bytes. And in this case, we see the word test, it's 4 bytes long. And then here we're passing the value 4. So here's the pointer to the function. Here's the length of the function. Same thing here, where we're passing it an integer to core.forLoop. Here, core.forRange, we're passing in the word gophers, which is 7 bytes long. Here it's the test race function doesn't have any particular length, which we see here the length is 0. And then here go test unsafe, the length is 3 bytes. So look for sim.runtime.newproc when you want to identify a function that's being called as a go routine. Now let's look a little bit at something interesting, just comparing again output from radare2 to the output that you will get from Go internal tooling. Here we have the when we are calling new proc, what's interesting here is that the location, we're loading the effective address of the function in question, and that it's being indicated by that is relative to RIP. In this case, in this other case where we're calling new proc, the effective address of that we're loading for the particular function that we want to call as a go routine, it's relative to the static base pointer, the pseudo register that we looked into earlier. So that's just something interesting to note. So what to look for as far as Go internal functions. So if you're looking for concurrency, get familiar with this particular functions. So Go runtime new object, Go make chan, which indicates that a new channel, Go channels are being used. Wait group, when you're passing functions to a wait group and calling those as Go routines. Defer proc stack, defer return when you are deferring specific functions. Any function that it's a cgo function, you're going to identify with underscore cgo underscore cfunc. And any functions that have to do with the Go garbage collector are going to be under sim.runtime as well. And these are two examples of them. GC write barrier for a barrier that is being written, and then a type mem move as we saw earlier. So the TLDR of that is read the manual, right? Now, Go error handling is something interesting to look for in Go binaries. This is because Go error handling it's very manual. So you have to do this, always be checking for adding extra code, what seems like extra code to check for errors. So when looking for bugs, it's worth taking the time to identify missing error handling logic, because the logic to check for errors is so manual in Go, then it is easy to mess up error handling. Now, keep in mind for this particular point that error is a Go interface. And a Go interface consists of two things: a pointer to a virtual table, which contains function pointers that point to virtual functions, and a value pointer. So this is how you can identify a Go error handling logic in Radare. So when checking for error does not equal nil, we load the vtable and error value. Then we test whether the value is nil, and we branch or return depending on the result. So this is the typical code that you will see. We call the set option function, which returns an error, and then we check whether that is not nil. which indicates that there's an error and that would return the error. And then we see here that particular situation where we call the function and then we load the vtable and the value for the error. We check for the error, and then in this case, if it is if there is not an error, then we continue. Otherwise, we return that particular error. So a quick note on working with strip binaries, Go binaries, of course. So the default build options, as I mentioned, do not strip dynamic symbols. Are not great at stripping binaries, right? So using Google build tools leaves a lot of useful symbols in the binaries. In those cases, in the cases where you are not able to identify a lot of these basic functions that we looked at, then the technique is usually to use R2 signatures when needed. So you will just write a simple hello world. You will load create a database with the signatures from that particular binary, and then you will match those against your strip binary. And then that way you can start identifying functions in your strip Go binaries. So let's say you want to research Go. Obviously, start writing some Go. And something interesting to play with is the Go pragmas. So let's say you are writing Go code and then you are not able to find the functions that you wrote. You might want to prefix your function with Go no split. Go no inline, sorry. And then you will use no Go no split to avoid telling so you can tell the Go runtime to not split the stack for your particular function. You can also look at this particular file in the Go source to look for this variable stack debug, which is set by default to 0. If you set it to 1, then when you run your Go binary, you will be able to see debugging messages that indicate when the stack for a particular function grows and shrinks. That's something interesting to look at. You can use the Go build tag M to print optimization decisions. That way you can, if you, for instance, write a defer function or a function as call it with defer, and you do not see call for defer, you might want to build it again with the M flag to make sure that Go didn't optimize that for you. You can also use go debug equal gtrace to better understand what the garbage collector is doing. You get some interesting messages telling you when the garbage collector is called and how many times. And you can use tools like gophers and gosec to check for bugs in your Go binaries. So those are very interesting tools to look into as well. So let's wrap up. The idea here then is to combine tools. What I want you to take away from this is when you start working with Go binaries, combine your usage of radare2 with tools, the Go tooling, particular obj DOM. That's gonna make your work a lot easier. Cross-referencing strings is not super fun. That's again because of the way that Go handles strings. It's not that big of a deal, but there are ways around that. So familiarize yourself with Go internals. That's a big takeaway from this. So look at and also understand how Go works with scheduling and how the garbage collector works. And if you are interested in looking for bugs, look for race condition bugs. Those are big ones. And when working with Go, look for handle errors and look for CGO, because if there is CGO, you might have you might be able to find some vulnerabilities like it's 1998. So questions, if you have any questions, please feel free to use the Google Slides questions, and I'll be available to answer any questions that you might have. I hope that you have enjoyed this. I'll be available for questions, like I said. Thank you, and have a good day.